Hello friends, welcome to my channel. Let's have a look at problem 300, longest increasing subsequence. So this is also a daily challenge problem. So in this video, we're going to share two formats of solutions. So the first solution is based on dynamic programming, and the second method is based on binary search with mathematical induction. So let's look at the statement. So given an integer array called nums, so we are required to return the length of the longest strictly increasing subsequence. So notice that here we are considering subsequence, not subarray. So here are three examples. So in example 1 and example 2, the outputs are both 4. So this is a such subsequence for example 1. And for example 2, we can think of 0, 1, 2, 3. In example 3, so this is an extreme case. All the numbers in the array are the same, therefore the return is 1. So the constraints for this problem are the following. The first one is the one that's important for us. So the length is bounded above by 2500. So this number, if you compute its square, it's not very large, and therefore a square term complexity method might work here. So also the nums array is not empty. So here is a follow-up, so which asks us to devise a n log n term complexity algorithm. So with that said, let's look at the method we're going to share. As we mentioned, so the two methods we are going to present are dynamic programming and binary search with mathematical induction. So our plan will be the following. First, we'll give the full solution using DP, and then we focus on explaining the binary search solution. So let's look at the item B here, the idea for dynamic programming solution. So this is actually very straightforward. So if we interpret the generic element for DP table, the DPI, so it's the length of the longest strictly increasing subsequence ending at index I. Then the DP update rule is the following. So we just compare the nums G for all G before I in order to update DPI. So if nums G is strictly less than nums I, then DPI is the maximum of the previous state and DPG plus 1. So plus 1 means that we can extend the longest strictly increasing subsequence ending at index G by 1. In other words, add the number nums I, right? So this is the DP update rule. So with that said, let's first finish this DP solution, and then we look at the binary search solution. So for this, we are going to first find the length of the nums array. So let's see, nums, and then we are going to initialize a variable called result, whose final state is what we want to return. So here I'm going to initialize this variable with value 1 because the nums array is not empty, right? So the length is at least 1. And meanwhile, we're going to initialize a DP table. So here I'm going to initialize like this. So it's an array with one element, then multiplied by m. So the reason we can do this is that 1 is immutable. So with that said, so we can do the main for loop. So for I in range m. So our goal is to update DPI, right? So for this, we are going to look at the previous index before I. So for this, we are going to do iteration for G in range. So we can use range up to I, or we can use this I minus 1, negative 1, negative 1. So this way, we actually look at this from right to left, but all the index G are less than I. So we're going to consider this condition if nums I is strictly larger than nums G. So if this is the case, actually we can extend the length of the longest strictly increasing subsequence ending at nums j by 1. In other words, we can append this number, right? So the dpi is nothing but the maximum of dpi, the previous state, plus dpj at 1, because we can extend the length by 1. So with that said, actually we finished the reset or update of dpi. Because we have a global variable called result, so we're going to update its state also. So it's the maximum of its previous state and current dpi. So with that said, actually we finished the main loop and the logic. What we are going to do is to return the result. So this is a full solution corresponding to the dynamic programming. Let's do a special case check first. So yeah, it passes a special case. Now let's do a generic case check. Yeah, it passes the generic case, but it's a little bit slow. So now let's look at the second solution. That is binary search-based solution, which is in response to the follow-up. So the idea actually is also straightforward, I would say. But if we actually we can make this solution very rigorous using mathematical induction. So here, before we look at the idea, here is a set remark. So the binary search actually is very powerful. So there are some specific usage patterns or paradigm for different problems. So we have a binary search playlist. You are welcome to check out that playlist. So in that playlist, basically we emphasize two things. First thing is that how to define Boolean function to produce order and monotonicity. The second thing is that how we do the search range shrinkage. So with that said, let's look at the idea here. So the idea is that when we traverse nums array, so we are trying to maintain a sequence that has the same length as the longest increasing subsequence so far. So the sequence we are trying to maintain in the process have the same length as the longest increasing subsequence, but maybe it's not exactly the longest increasing subsequence we want, because the problem actually is to return the length. So to do this, every time we reach some nums I, so we do a binary search on the maintained sequence. Let's call it aux. So if we return the index is exact the length, then we just need to append the current number. Actually, this condition corresponding to the fact that the nums I is larger, strictly larger than the last element in the sequence we maintain. So otherwise, we replace the aux index by the current number. So that's the overall idea. So actually, after we finish the traversing the nums, so aux will always have the same length as the longest increasing subsequence of nums. So here is a specific walkthrough. So in this example, so if we initialize this one by empty, then we look at each number. So when we look at 10, so we add 10. When we look at 9, so actually we found that 9 is less than 10, right? So we replace this 10 by 9. And then we look at 2, so we replace 9 by 2. And then if we look at 5, actually we add 5 to the state, right? So if we look at 3, actually, 3 is less than 5, so we replace 5 by 3. So when we look at 7, so actually we append 7 to 3. We get 237. And if we look at 4, actually this 4 does not increase the length. So we're going to replace 7 by 4. So if we look at 18, actually 18 is larger than 4, so we are going to append. So overall, we have an aux, the final state has length 4. Therefore, the length of the longest increasing subsequence is 4. So that's a walkthrough, and actually up to now we can write the code, but here is some extra thing that actually can make this procedure rigorous. So in this procedure, actually we do two operations. So first operation is append, and second operation is replace. So actually we can prove the following property. So assume the LLRS is the length of the longest increasing subsequence for nums from 0 to this index. So actually using mathematical induction, we can prove at each index I, so this length of the sequence we maintained equals the length LLRSI. So this is actually very easy to prove. So first, when I equals 0, so this property is trivially true because both the two lengths are 1. Then we want to use mathematical induction. Then assume this property holds for any g less or equal than I. Then we want to show this p holds for I plus 1. So this is actually simple, right? So we consider two cases. First, if nums I plus 1 is strictly larger than the last element in the aux, then we use append operation, right? Both the two lengths actually incremented by 1. For sure, they are equal. Otherwise, the two lengths does not increase. Therefore, p still holds. So overall, actually, we proved the property. But here, maybe you have a question. Why we use replace operation? The answer actually is simple. So to maintain sorted order for doing binary search. So with that said, I guess we want to end this idea explanation with some caution. So this algorithm above actually is only useful for getting the length of the subsequence we are interested in. We cannot use this algorithm to retrieve the actual subsequence, right? So with that said, I guess we are ready to write the specific code. So let's copy this function signature. I'm going to call this one v1. So this actually we also first let's add some annotation. So binary search. So here what we want to do first is the length of nums, just for convenience, and we are also going to initialize a list. So we first put the first number of nums into this list, and then we iterate from index 1. So for I in range 1 to n, first I will write in a more straightforward way, and then we change the code a little bit. So the first is that if nums I is strictly larger than aux -1, the last element in the current aux, then we are going to append this current number, right? So we are going to append this nums I. So otherwise, what we want to do actually is to do a binary search. So let's call this idx. So here I'm going to call some module. So from bisect import bisect left. So let's see, because in the procedure we actually maintain the sorted order for aux, so we can do bisect left. So we are searching from this one, and this is the scope we are doing the search, binary search, and the candidate we are looking at is nums I, right? So this index is the following. So left the index, all the numbers is strictly less than nums I. Then what we are going to do is that, so because we have this if condition, so this idx is less than the length of this one. So we're going to reset, right? So we're going to reset aux idx equals nums I. So this way, actually, the aux is again in sorted order. So with that said, I guess we are ready to return the length of aux after the for loop. So this length will be the same as the subsequence length we are interested in. So let's first do a special case check. So yeah, it passes a special case. Now let's do a generic case check. Yeah, it's much faster. So here, let me write in another format just to make it more clear. So let me copy this thing again. So I'll call this one v1. Oh, sorry. So let's copy it again. So let's call this one v2. And here, actually, when we do this, actually we can directly call this part. So and then we can check if idx equals the length of aux, it means that nums I is strictly larger than the last element in aux. So we're going to aux append nums I. And otherwise, so we do the replacement, and then we can return this one. So let's do a generic case check directly. Yeah, it passes the generic case. I guess with this version of solution finished, that's all about this video. Thank you very much.